Hello, digital learners. This is your note set for air masses and fronts. So I'd like to start with a crash course video, and I will warn you that she does talk very quickly. We are going to unpack this, but she goes over a lot of the important information that we found with our Heating Earth Surface Lab. So let's take a look.
You know who we haven't hung out with in a while? This guy. What's up, son? You remember that the sun provides the Earth with energy, or warmth. And you know that the Earth's surface is made up of different types of land and water. Now, it would probably make sense that these different landforms and bodies of water would absorb, or soak up, the sun's heat at different rates, right? Well, you're right, it does. But which one absorbs more of the sun's energy? Land or water? And more importantly, why? Let's start with a refresher course on the sun. We know the sun as the star at the center of our 8-planet solar system that provides us with heat. We also know that heat is a kind of energy that warms things. This energy starts in the sun's core. It travels very slowly to the sun's surface before it takes a super speedy trip to Earth in the form of light and heat. You and I can see and feel that energy as sunlight. But how much of all of that energy that the sun cooks up actually makes it to us and the land and the water on Earth? I know what'll help us figure this out. A delicious pie graph. Essentially, 100% of the energy that warms the Earth comes from the sun. About 20% of that energy is absorbed by the Earth's atmosphere and clouds. Nearly 30% never makes it to the Earth's surface, and instead is bounced back out to space by clouds and different gases and particles in the atmosphere. But about half of the sun's incoming energy, just over 50%, is absorbed by the Earth's surface. That is, its land and water. Well, when that 50% of sunlight gets to Earth, the land and water absorb or soak up its warmth. But, like I mentioned before, they absorb this heat at different rates. So which one absorbs more of this heat? It's time to play land versus water. Okay, let's think of a place somewhere on Earth where land meets water. Is anyone else thinking beach? Let's take a look at how the sun's energy is absorbed by both the land and the water on our little beach. The land is all of the sand you see right up to where the shoreline starts, and the water is the shoreline and all of the ocean behind it. So, what happens when the sun's energy hits the land? Well, the sunlight is absorbed by the sand, making the sand warm or even hot to the touch. The longer the sand is exposed to the sun, the more heat it absorbs. Now, let's take a close look at the land. It's darker in color than the water, and generally, darker colored objects absorb more heat than lighter colored objects. So, when the same sunlight that warms the sand hits the water next to it on our little beach, the water doesn't soak up quite as much of that energy as the land did. Instead, the water reflects more of it. Reflection is the opposite of absorption. Instead of being absorbed by the water, some of the sun's energy is bounced or reflected off of the water in a different direction. And lighter colored things tend to reflect more heat than darker colored things. This is why the water that's been under the same sun as the sand all day doesn't feel quite as hot as the sand. So, when you get hot after playing around on the sand all afternoon, and I really hope you've been wearing sunscreen, you can wade off in the water to cool off. That's what the beach is all about, right? So, it looks like Team Land wins, by which I mean it absorbs more of the sun's energy. And the land absorbs more energy because darker colored objects absorb more heat than lighter colored objects. And light colored things, like the water, reflect more of the sun's energy. Hey, where'd the sun go? Oh, right, outside. Sounds like a plan to me.
All right, so I told you she was going to talk pretty quickly, but let's go ahead and unpack this. So our expected outcomes from the Heating Earth Surface Lab. Now, please keep in mind that this is not a perfect lab. This is not a perfectly controlled lab space. It's a classroom, okay? So what we would expect to see is that because of the soil's dark color, it should have warmed up the fastest. The sand, because of its light color, should have cooled down the fastest. And the water probably did a whole lot of not much. The water is going to be slow to warm up, but it's also going to be slow to cool down due to something called specific heat. And water has high specific heat, which means it takes a lot of energy to heat it up, but it also takes a lot of energy for it to cool back down. And you've experienced this. So I want you to think about going to the beach. You haven't gotten there super early. Maybe you're rolling in around 10 or 10:30 in the morning. And think about your feet on the sand. Are they burning up? Because I know mine do. And where do you run to? You run to the water, because the sand is going to have heated up faster than the water did. Now, let's flip it. Let's go take a nice walk along the beach at night. How does the sand feel to your feet now? Yes, it should feel cold. And if you wanted to warm them up, you would go put them in the water. So just keep in mind that black absorbs more heat than white, or dark colors absorb more heat than light colors do. This is why we don't typically wear dark colored shirts to the theme parks in the summer. We typically wear light colored or white shirts. This is also why many people in Florida don't drive dark colored cars with dark colored interiors, because we know that they're going to get super hot, especially in our long summers. So this has some implications, and this is where your notes for the day are going to pick up. So the unequal heating of Earth's surface leads to convection. Remember that convection is the movement of a fluid, because as heat or temperature rises, I should say, the density is going to decrease and less dense objects will float. In our atmosphere, this is going to result in the formation of an air mass, or kind of a blob of air, with similar temperature and moisture content throughout. Remember that because this is a screencast, if you need to pause me to complete your notes, go right ahead. So let's take a look at this. Here's our tiny beach for the day. And think back, it's maybe 10 or 10:30, you're taking your stuff, you want to get it all set up. And the warmest air is going to be right above the sand, because remember, your sand is hotter than your air. So the air right above the sand is going to heat up and become less dense. Well, then what is it going to do? It's going to rise. But air is a gas, so it's not just going to leave this nice empty void. New air is going to rush in from over the water, where then it is going to heat up, and then it will rise. And then more cold air is going to rush in and warm up and rise. And what does this suddenly look like? You should say it looks like a convection cell. And if you did, you are absolutely correct. So air masses get their characteristic temperature and moisture based on where they form. So take a look at the two air masses in this image. You'll see that we have air mass 1 and air mass 2. So which of these do you think is going to be colder? Yes, you should say air mass 1. Which of these will be warmer?
Henry Bello, please report to Cosmo. Henry Bello, please report to Cosmo.
Sorry about that. You should also take a look at the amount of water around these air masses. So for air mass 1, we have mostly continent, mostly land. Yes, there are the Great Lakes, but because it's mostly land, there's not going to be very much moisture content or humidity. So this is going to be fairly dry. Air mass 2, on the other hand, is forming over the Atlantic Ocean and the Gulf of Mexico, so it's going to have a lot of moisture or a lot of humidity. So in this image, we are able to see that warm air masses are at the equator and cold air masses are going to be up at the poles. That little dark spot is just a lack of data. Now remember, with thermodynamics, which means the laws of how heat moves, it's going to try to constantly move from warm to cold. Okay, the equator wants to make the poles warmer. Earth wants to be at equilibrium, wants to be at the same temperature. But as that warm air moves north to try to heat up the poles, that creates room back down at the equator for more air. And what's going to push in? Cold air. And suddenly, again, we get warm air moving towards the poles, cold air from the poles moving towards the equator, and it looks again like a convection cell. So to describe these air masses, we use letters to talk about the humidity and the temperature of where these air masses form. So the naming convention, I want you to throw everything you know out the window. We are actually going to start with our lowercase letters in this case. So lowercase c means continental, which means it's forming over land. So it's going to be low moisture, low humidity. It's going to be dry. Lowercase m stands for maritime. Remember that our prefix mar means ocean, like submarine or Maria on the moon. Okay, so ocean, it's wet, it's humid, there's a lot of moisture content. Our capital letters are going to tell us about temperature. Capital T means tropical, that means it's warm, think of your palm trees. Capital P means polar, it's cold. For whatever reason, I think of penguins. So take a look at your notes. You should have two practices before this image. You should have one that says CP. So that is going to be continental polar. So it's going to be low humidity or low moisture content and cold. The other one is going to be MT. That is maritime tropical. So it is going to be high humidity, warm temperatures. So typically living here in Florida, we are living with MT air masses, warm and humid. So please pause me, and I want you to do your best here to label what these bubbles or air masses would be. Remember to start with the lowercase letter for humidity and then go to the capital letter for temperature. Okay, welcome back. Let's see how you did. So along the top, we have maritime polar on either side, but then continental polar in the middle. And along the bottom, we have three maritime tropicals. We have one in the Pacific, one in the Gulf, one in the Atlantic. And then over that kind of desert southwest, we have a continental tropical. So here's a world map of what to expect with these air masses. And this is about the point that some of you who are super observant notice that there's an E. That E just means equatorial. So it's going to have a temperature and humidity content that are fairly close to one another and fairly consistent. And then we'll also see the A's up top. So these stand for Arctic, or the double A for Antarctic. And now we're talking very, very dry but frigidly cold. But for most parts of the world, the M and the C and the T and the P cover what we need them to. So now when these two different air masses collide, they're not going to do it nicely. Because they are two different temperatures and two different moisture contents, they have different densities. And so they are going to form fronts. So follow along with me here. We have uneven heating of Earth's surface, which leads to convection. Convection leads to air masses. Two air masses colliding lead to fronts. And fronts lead to changes in the weather. So weather all comes back to the fact that Earth's surface is not evenly heated. So here is a quick video that I'm going to show you about the different types of fronts. You do not need to take any notes from this video.
Air masses are large regions of air that have similar characteristics from the surrounding area. Air masses can form over places like warm tropical oceans, cold, dry polar regions, or even dry deserts. As air masses move over different regions, they will gradually take on the characteristics of the new region and begin to change. As air masses move across the Earth, they will eventually run into each other. The boundaries between these two air masses are referred to as fronts. Fronts are labeled in reference to the relative temperature of the air that is approaching and replacing the existing air mass. There are 4 types of fronts: warm fronts, cold fronts, stationary fronts, and occluded fronts. A warm front occurs when a warm air mass overtakes an air mass of a colder temperature. Warm fronts usually move slowly, around 10 to 25 miles per hour, and have a gradual slope that will slide over the top of a cooler air mass and move it out of the area. Warm fronts usually contain high humidity and have more stratiform or layered clouds along the frontal boundary. Drizzle and decreasing visibility will be present as temperatures rise. Once the front passes, rain showers are possible, followed by a gradual clearing. A cold front occurs when cold, dense air overtakes warmer air. Cold fronts move faster than warm fronts, averaging 25 to 30 miles per hour, but can go as fast as 60 miles per hour. Cold fronts stay close to the ground and have a steeper angle than a warm front. They will move across the ground and lift existing air at a very rapid rate. This rapid upward motion will cool the air and form cumulus clouds, which could eventually develop into thunderstorms or even form a line of thunderstorms called a squall line. Once the front passes, the weather will clear and improve with general wind flow from the west-northwest. A stationary front occurs when two air masses meet, but neither one moves the other out of the way. Stationary fronts can have a combination of weather from both a warm and cold front. These fronts can oscillate, but will generally linger around for several days before one of the air masses pushes the other air mass out of the way. The last type of front is called an occluded front. Occluded fronts form when a fast-moving cold front catches up to a slower-moving warm front. Cold front will then lift up the warm front and eventually interact with the air that is in front of the warm front. This stacking of fronts can give rise to a variety of weather conditions, from fog to thunderstorms.
All right. So fronts are boundaries between two air masses. And this is where we are going to get weather. So whenever you see a weather map, we do have a rule, and the convention is that the direction the bumps or the half circles or triangles are pointing is the direction that the front is moving. So we have 4 types of fronts. I want for you to write in the name of the front and also be sure to record what the symbol is in your notes. So a cold front is when cold air moves into an area, and we denote that with blue triangles. So based on the convention, the front, if it were truly happening on this slideshow presentation, would be trying to move towards the top of your screen. A warm front is when warm air moves into an area, and it's going to be exactly opposite for its symbol. It's going to be red, and it's going to be half circles. Stationary fronts. Stationary refers to movement, and if something is stationary, it's stalled, it's not moving. So this is when it's like a tug of war, and neither the warm nor the cold air mass are actually going to move. So based on this one, our warm air mass would be trying to move towards the top of your screen, while your cold air mass would be trying to move towards the bottom of the screen. And then last but not least, we get an occluded front. And this happens when a warm air mass gets caught in between two cooler ones. It kind of makes a warm air mass sandwich. And notice that we've combined the two symbols here because that warm air mass is going to try to heat up the two symbols. So what happens when we mix red and blue? We get purple. So here's the weather map. You can see all of these symbols on it. And now you know what they mean. And so here are some animations. Notice that with the cold front, it comes in and it comes in very quickly, and it tends to kind of steamroll because it's dense, so it can stay low. But where it mixes with the warmer air, we are going to get precipitation. And generally this is going to be in the form of thunderstorms. Cold fronts can move very, very quickly, and they happen over a short distance. Warm fronts are very different behaving because they are the less dense. So they have to be very polite about coming in. They can't steamroll through that air because they're warmer, they're less dense. So they're going to truly kind of come in and slide over. And the first sign that we're going to get that a warm front is approaching is some of these high-flying clouds up top. Notice that the rain doesn't come until much later, whereas with the cold front, the rain is right at the front of it. It's right at the beginning. Whereas with the warm front, the rain and the precipitation are going to come in behind. So I hope that this has helped. Just one of the key things is remember that the unequal heating of Earth's surface leads to air masses. Air masses colliding leads to fronts, and fronts brings changes to our weather.